You are standing on ground that should not exist. Every second, the quantum vacuum, the empty space between your atoms, between galaxies, between everything, seethes with energy. Virtual particles blink in and of existence trillions upon trillions of times per second. That energy, according to quantum field theory, should be violently repelling every piece of matter in the universe. The prediction, calculated from first principles, is that the vacuum energy density should be roughly 10 to the 120th times larger than what we observe. This is not a small discrepancy. This is the cosmological constant problem, the worst prediction in the history of physics. And it means that, by every calculation we trust, the universe should have torn itself apart long before the first star ignited. Yet, here you are. The galaxies hold together. Space expands, but gently, accelerating at a rate so modest that astronomers did not confirm it until 1998. Something suppresses the vacuum energy by 120 orders of magnitude. No one knows what. No proposed mechanism comes close. And the silence of that cancellation, its precision, its inexplicability, sits at the center of modern cosmology like a question physics cannot answer. Within the next 2 hours, you will see exactly how quantum field theory generates that catastrophic prediction, and why every attempt to resolve it has failed. You will understand what the accelerating expansion of the universe reveals about the vacuum energy that exists, and why that measured value is so impossibly small. There is a subscribe button below this video, quietly waiting. If deep explorations like this one hold your attention, subscribing helps them reach more minds who value rigor over comfort. Now, the descent. The vacuum is not empty. You were taught, perhaps, that a vacuum is the absence of everything. No particles, no fields, no energy. Quantum field theory destroyed that picture in the 1920s. The vacuum, in quantum mechanics, is the lowest energy state of a field, and that state is not zero. It cannot be zero. The Heisenberg uncertainty principle forbids a field from having both a perfectly defined position and a perfectly defined momentum. A field at absolute rest would violate that principle. So, every field, the electromagnetic field, the electron field, the quark field, fluctuates, even in its ground state. Particles appear and disappear. Energy spikes and vanishes. The vacuum hums. These are not real particles in the sense that you can catch one and hold it. They are virtual particles, quantum fluctuations that exist for intervals so brief that direct measurement cannot resolve them. Intervals governed by the energy-time uncertainty relation. That relation, derived from the Heisenberg principle, states that the uncertainty in energy, delta E, multiplied by the uncertainty in time, delta T, must be greater than or equal to Planck's constant divided by 2. Delta E times delta T greater than or equal to h bar over 2, where h bar is the reduced Planck constant, approximately 1.055 times 10 to the minus 34 joule seconds. This equation permits a pair of particles, say an electron and a positron, to appear, borrowing energy from the vacuum, as long as they annihilate each other and return that energy within a time interval short enough that the product, delta E times delta T, remains above the threshold. The shorter the interval, the larger the energy fluctuation allowed. At timescales approaching the Planck time, roughly 10 to the minus 43 seconds, the fluctuations can be enormous. These fluctuations have measurable consequences. They shift the energy levels of hydrogen atoms, an effect called the Lamb shift, first measured by Willis Lamb in 1947. They generate a tiny attractive force between two uncharged metal plates placed close together in a vacuum, the Casimir effect, confirmed experimentally by Marcus Sparnay in 1958 and refined in dozens of experiments since. Virtual particles are not speculation. They are confirmed features of the quantum vacuum, and their effects match the predictions of quantum field theory to extraordinary precision. In some cases, agreement to 1 part in a billion. But those effects are local and tiny. The cosmological constant problem concerns the total energy density of the vacuum across all of space, and there the predictions spiral out of control. What does it mean that the vacuum has energy density? Energy density is energy per unit volume. If the vacuum fluctuates, and those fluctuations have energy, then empty space itself carries energy in every cubic meter. Quantum field theory provides a way to estimate that energy density. Consider a single quantum field, say the electromagnetic field. The field can be thought of as a collection of harmonic oscillators, one at each point in space, each oscillating at a different frequency. The ground state energy of a single quantum harmonic oscillator is 1/2 h bar omega, where omega is the angular frequency. Sum the ground state energies of all oscillators across all frequencies, and you obtain the vacuum energy density of that field. The sum diverges. As frequency increases, so does the energy per oscillator. There is no natural cutoff, no frequency at which the field stops contributing. Physicists impose a cutoff by hand, arguing that quantum field theory cannot be trusted at energies above some threshold where new physics must take over. The most conservative choice is the Planck energy, roughly 10 to the 19 giga-electron volts, corresponding to the Planck length, roughly 10 to the minus 35 meters, the scale at which quantum gravitational effects become significant, and space-time itself is expected to fluctuate. Integrate the vacuum energy density up to the Planck scale, and the result is a number on the order of 10 to the 113 joules per cubic meter. Convert that to the units cosmologists use, energy density in terms of the critical density of the universe, and you obtain a vacuum energy density roughly 10 to the 120 times larger than the value inferred from cosmological observations. That observed value comes from measurements of the accelerating expansion of the universe. In 1998, two independent teams, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Riess, announced that distant Type 1a supernovae were dimmer than expected. Type 1a supernovae are thermonuclear explosions of white dwarf stars that have accreted mass from a companion until they reach the Chandrasekhar limit, about 1.4 solar masses. The explosion is remarkably uniform in brightness, making these supernovae useful as standard candles, objects whose intrinsic luminosity is known, so that their observed brightness reveals their distance. The teams measured supernovae at redshifts between 0.3 and 1.0, corresponding to look-back times of 3 to 8 billion years. The supernovae were dimmer than the predictions of a universe expanding at a constant rate. Dimmer means farther away. Farther away, for a given redshift, means the expansion has accelerated. Something is pushing space apart, and that something behaves like a cosmological constant, a configuration of energy with negative pressure spread uniformly through space, whose density does not dilute as the universe expands. The density inferred from those supernova observations, combined with measurements of the cosmic microwave background radiation and the large-scale distribution of galaxies, is approximately 6 × 10⁻10 joules per cubic meter. Call this rho sub obs. The quantum field theory prediction, call it rho sub QFT, is roughly 10⁻113 joules per cubic meter. The ratio is rho sub QFT over rho sub obs approximately equals 10⁻120 power. That factor, 1 followed by 120 zeros, is the cosmological constant problem. Quantum field theory predicts a vacuum energy density 120 orders of magnitude larger than what we measure. If the prediction were correct, the repulsive effect of that energy would have driven the expansion so violently that no structure, no galaxies, no stars, no atoms could have formed. The universe would have blown itself apart in a fraction of a second. It did not. You exist. The vacuum energy is tiny. Something cancels the quantum contribution almost perfectly, but not quite perfectly, because the observed vacuum energy is not exactly zero. It is small, but positive. And no one knows why. Think about that ratio for a moment. Consider 2 surveyors hired to measure the same river, one from the source, one from the mouth. If they disagree by 9% after both recheck their work 3 times, you stop questioning the instruments and start wondering whether they measured the same river. Now imagine they disagree by a factor of 10⁻120. That is not a measurement error. That is a signal that something fundamental is missing from the theory. What attempts have been made to resolve this? The first instinct is to argue that the vacuum energy does not gravitate, that the quantum fluctuations, though real, do not contribute to space-time curvature. But general relativity does not permit this. Einstein's field equations relate the curvature of space-time to the total energy-momentum content of space, and energy is energy. The equations do not distinguish between the energy of matter and the energy of the vacuum. If the vacuum has energy density, that energy curves space-time. The theory demands it. A second approach is supersymmetry. Supersymmetry is a proposed symmetry between fermions, particles with half-integer spin, and bosons, particles with integer spin. In a supersymmetric theory, every fermion has a bosonic partner, and every boson has a fermionic partner. The vacuum energy contributions of bosons are positive. The contributions of fermions are negative. If supersymmetry were exact, the contributions would cancel perfectly, and the vacuum energy would be exactly zero. But supersymmetry is not exact. If it were, we would have detected the superpartners of known particles, the selectron, the squark, the photino, and we have not. Experiments at the Large Hadron Collider, which has been smashing protons together at energies up to 13 tera-electron volts since 2015, have found no evidence of supersymmetric particles. If supersymmetry exists, it is broken at some energy scale, and a broken symmetry does not cancel the vacuum energy. It merely shifts the problem. Why is the breaking scale tuned such that the leftover vacuum energy is 10 to the 120th times smaller than the natural scale? The fine-tuning remains. A third approach is the anthropic principle. The anthropic principle, in its weak form, states that the observed properties of the universe must be compatible with the existence of observers. If the vacuum energy were much larger, the universe would have expanded so rapidly that galaxies could not form, and life, at least life as we understand it, would not exist to observe anything. We observe a small vacuum energy because only universes with small vacuum energies contain observers to make the observation. Steven Weinberg, in a 1987 paper, sharpened this argument. He calculated that if the vacuum energy density were more than about 100 times its observed value, the universe's expansion would prevent the formation of gravitationally bound structures. Galaxies would not form. Stars would not ignite. Weinberg argued that this placed an upper bound on the vacuum energy, and that the observed value, while small, is not absurdly small in the context of that bound. It is merely within the narrow anthropic window. This argument requires a multiverse. If only one universe exists, the anthropic principle is not an explanation. It is merely a restatement of the problem. But if an enormous ensemble of universes exists, each with a different value of the vacuum energy, then the fact that we find ourselves in a universe with a small value is no more surprising than the fact that we find ourselves on a planet with liquid water and an oxygen atmosphere. We are here because here is where conditions permit life. The multiverse is not a prediction of quantum field theory. It is a prediction of certain inflationary cosmology models and of string theory. String theory, which attempts to unify quantum mechanics and general relativity by replacing point particles with one-dimensional strings, allows for a vast landscape of possible vacuum states. Estimates range from 10 to the 500th to 10 to the 10,000th distinct configurations, each corresponding to a different set of physical constants, including the vacuum energy density. If eternal inflation populates that landscape, generating a bubble universe for every vacuum state, then the anthropic argument has a framework. We observe a small vacuum energy because we could not exist in the universes where it is large. But the multiverse is not observable. By definition, other universes are causally disconnected from ours. Their light cannot reach us, their particles cannot interact with ours. No measurement we perform can confirm or rule out their existence. The anthropic explanation, even if correct, is not testable in the way that physics traditionally demands. It shifts the question from "why is the vacuum energy so small?" to "why does the string theory landscape exist?" and "why does eternal inflation populate it?" Those questions may be no easier to answer. What does it mean that the most successful theory in physics makes a prediction wrong by 120 orders of magnitude? And the best explanations we have invoke either undetected symmetries or unobservable universes. Let us look more closely at what the accelerating expansion reveals. The evidence for acceleration rests on distance measurements. In cosmology, distance is not straightforward. Light from a distant galaxy has traveled for billions of years, during which the universe has expanded. The space between us and the galaxy has stretched. As space stretches, so does the wavelength of light passing through it. A photon, emitted in the ultraviolet, arrives in the infrared. This stretching is redshift, and it is quantified by the redshift parameter Z, defined as the fractional increase in wavelength. Z equals lambda sub obs minus lambda sub emit over lambda sub emit, where lambda sub obs is the observed wavelength and lambda underscore emit is the emitted wavelength. A redshift of Z equals 1 means the wavelength has doubled. The supernova teams measured redshifts up to Z equals 1, corresponding to light emitted when the universe was roughly half its current age. For a given redshift, the distance to the object depends on the expansion history of the universe. If the expansion is decelerating, as it would be in a universe dominated by matter and radiation, the object is closer than it would be if the expansion were constant. If the expansion is accelerating, the object is farther away. The supernovae were farther away than expected for a decelerating universe. The simplest explanation, and the one that fits all subsequent data, is that the expansion is accelerating, driven by a component with negative pressure. Pressure, in cosmology, is not the pressure you feel when you squeeze a balloon. It is a component of the stress-energy tensor, the mathematical object that appears on the right-hand side of Einstein's field equations. A fluid with positive pressure, like ordinary matter or radiation, resists compression. A fluid with negative pressure resists expansion, or, equivalently, pulls on itself. But in the context of general relativity, negative pressure has a gravitational effect opposite to that of positive energy density. Positive energy density attracts, negative pressure repels. A component with negative pressure drives accelerated expansion. The simplest candidate is a cosmological constant, denoted by the Greek letter lambda. A cosmological constant is a term Einstein added to his field equations in 1917, hoping to obtain a static universe. The equations, without that term, predicted that the universe must either expand or contract. Einstein, who believed at the time that the universe was static, introduced lambda to balance the attractive pull of matter. When Edwin Hubble discovered in 1929 that galaxies are receding, that the universe is expanding, Einstein called lambda his greatest blunder and removed it from the equations. But the cosmological constant never went away. Mathematically, it is a free parameter in the field equations. Physically, it corresponds to a uniform energy density in the vacuum, with an equation of state, a relation between pressure and energy density given by P equals minus rho c squared, where P is pressure, rho is energy density, and c is the speed of light. This equation of state, P equals minus rho c squared, is unique to a cosmological constant. It produces negative pressure equal in magnitude to the energy density, and it does not dilute as the universe expands. As space stretches, the energy density of matter decreases, more volume, same amount of matter, but the energy density of a cosmological constant remains fixed. That property drives accelerated expansion that grows exponentially over time. The supernova observations, combined with measurements of the cosmic microwave background by the Wilkinson Microwave Anisotropy Probe and the Planck satellite, and large-scale structure surveys like the Sloan Digital Sky Survey, converge on a model called ΛCDM. Lambda stands for the cosmological constant. CDM stands for cold, dark matter, the unseen mass that accounts for roughly 27% of the universe's total energy budget. The remaining 68% is dark energy, the term for whatever drives the acceleration. The cosmological constant is the simplest form of dark energy, and so far it fits all observations. But the fit raises more questions than it answers. Why is the vacuum energy density so small? Why is it comparable to the matter density today when the two evolve so differently? Matter density diluting with expansion, vacuum energy density staying constant. This is the coincidence problem. For most of the universe's history, vacuum energy was negligible. Matter and radiation dominated. Only in the last few billion years has vacuum energy become significant. We happen to live in the brief era when matter density and vacuum energy density are within a factor of a few of each other. Why now? The anthropic answer, again, is that structure formation requires this timing. If dark energy had dominated earlier, galaxies would not have formed, and observers would not exist. But that answer defers the question. It does not explain why the universe is built such that observers arise at all, or why the parameters fall within the narrow range that permits it. Other models of dark energy exist. Quintessence is a proposed scalar field similar to the Higgs field that rolls slowly down a potential energy curve. Unlike a cosmological constant, quintessence can evolve over time, and its equation of state need not be exactly p equals minus rho c squared. Observational constraints allow some variation. The parameter W, defined as the ratio of pressure to energy density, could differ slightly from -1. But current data are consistent with W equals -1 to within a few percent. No deviation has been confirmed, and quintessence introduces its own fine-tuning problems. Why does the field start with the right initial conditions? Why does the potential have the right shape? The problem shifts, but does not vanish. What does it mean that the vacuum energy, whatever its origin, happens to have the precise value that allows structure to form, life to arise, and observers to measure it? Before I continue, take a moment to consider what this implies. The vacuum energy could have been anything. The range of possible values spans 120 orders of magnitude, from the Planck scale down to 0. The observed value sits at the very bottom of that range, within the narrow anthropic window Weinberg identified. 1 part in 10 to the 120th. If you were to choose a random number from a pool that large, the probability of landing within the observed range by chance is incomprehensibly small. Yet here it is. Does that improbability demand an explanation, or does it merely reflect the fact that we could not exist to ask the question if the value were different? Let us examine what happens when the vacuum energy is not small. Imagine a universe identical to ours in every way, except the vacuum energy density is 10 times larger. 10 times is nothing, a rounding error on the scale of the cosmological constant problem, but it is enough. In such a universe, dark energy begins to dominate the expansion earlier. The universe is younger when galaxies stop forming. Fewer stars ignite. Fewer planets form. The window for life to arise narrows. Now increase the vacuum energy density by a factor of 100. Dark energy dominates before the first galaxies collapse. Density fluctuations, the small variations in matter density seeded by quantum fluctuations during inflation, never grow large enough to overcome the accelerated expansion. The universe expands smoothly, diluting matter to insignificance, and remains empty forever. No stars, no planets, no observers. Increase it by a factor of 1,000, and the universe lasts only a few million years before the expansion tears apart any structure that might have begun to form. Increase it further, and the universe ends almost as soon as it begins, stretched so thin that even individual atoms would be ripped apart by the phantom energy of the vacuum. Weinberg's calculation set the upper bound at roughly 100 times the observed value. Above that, the universe is sterile. Below that, structure formation proceeds. The observed value is small, but it is not absurdly small within the context of the anthropic window. It is merely the value a universe with observers must have. But the window itself is narrow. Picture a dial with 120 tick marks, each representing an order of magnitude in vacuum energy density. The dial can be set anywhere from 0 to the Planck scale. The anthropic window spans perhaps 2 or 3 tick marks at the very bottom. The dial sits within that range. Is that chance? Is it selection from a vast ensemble? Is it something else? The ΛCDM model does not answer this. It describes what the universe is doing, accelerating, and parameterizes that acceleration with a cosmological constant. But it does not explain where the constant comes from, or why it has the value it does. ΛCDM is a phenomenological model. It fits the data, but it is not a theory of dark energy. It is a placeholder. What alternatives exist? One possibility is that general relativity itself is incomplete. The field equations might require modification at cosmological scales. Modified gravity theories, such as F of R gravity or scalar tensor theories, attempt to reproduce the effects of dark energy by altering the left-hand side of Einstein's equations, the curvature terms, rather than adding a new component to the right-hand side. If gravity behaves differently on scales of billions of light years, the accelerated expansion could be a consequence of geometry rather than vacuum energy. These theories face stringent observational constraints. The detection of gravitational waves from a neutron star merger in 2017, event GW170817, provided a powerful test. The gravitational wave signal arrived at Earth within 1.7 seconds of the gamma-ray burst from the same event. Gravitational waves, in general relativity, travel at the speed of light. Many modified gravity theories predicted a different speed, a delay or advance of hours or days over the 130 million light-year distance. The near-simultaneous arrival ruled out broad classes of modified gravity models. Those that remain must reproduce the predictions of general relativity to extraordinary precision at solar system and galactic scales, while diverging only at cosmological distances. The parameter space is narrow. Another possibility is that the vacuum energy is not constant but dynamic, evolving as the universe expands. Models of quintessence, K-essence, and other dynamical dark energy scenarios introduce scalar fields whose energy density changes over time. These models can, in principle, alleviate the coincidence problem, why dark energy dominates now, by constructing potentials that cause the field to begin rolling recently in cosmic history. But they do not solve the cosmological constant problem. The initial conditions and the shape of the potential must still be finely tuned to produce the observed acceleration. The tuning is shifted from one parameter to another, not eliminated. A third possibility is that the vacuum energy is exactly zero, and the acceleration is an artifact of inhomogeneity. The universe, on scales smaller than 1 billion light-years, is lumpy. Galaxies cluster. Voids stretch between clusters. If the expansion rate differs between dense regions and empty regions, as it does in general relativity, where local curvature depends on local matter content, then the average expansion rate, measured by observing distant supernovae, might not reflect the global expansion rate. This is the back reaction hypothesis. If the effect is large enough, it could mimic the signature of dark energy without requiring a cosmological constant. Decades of work on back reaction have not produced a model that fits the data. The consensus among cosmologists is that back reaction effects are too small to explain the magnitude of the observed acceleration. The universe, averaged over sufficiently large scales, is remarkably homogeneous, and the ΛCDM model, which treats it as such, fits observations from the cosmic microwave background to the large-scale distribution of galaxies with percent-level precision. Inhomogeneity might contribute small corrections, but it cannot replace dark energy. So the tension remains. Quantum field theory predicts a vacuum energy 120 orders of magnitude too large. General relativity requires that vacuum energy to gravitate. Observations show that space is accelerating, driven by something that behaves like a cosmological constant with a suspiciously small value. No known mechanism cancels the quantum contribution. No symmetry enforces the cancellation. No dynamical process explains why the value is what it is. What does it mean that the vacuum is calm enough for you to exist, but no calculation explains why? Let me bring us to the edge of what the data constrains. The measurements that revealed accelerated expansion rest on 3 independent pillars. The first is supernova distance data. Type 1a supernovae used as standard candles to trace the expansion history. The second is the cosmic microwave background, the relic radiation from 380,000 years after the Big Bang, whose temperature fluctuations encode information about the geometry and content of the universe. The third is baryon acoustic oscillations, the imprint of sound waves in the early universe frozen into the large-scale distribution of galaxies. All 3 agree. The universe is spatially flat to within measurement uncertainty. Matter accounts for roughly 32% of the total energy density. Dark energy accounts for 68%. The equation of state parameter W is consistent with -1, the value for a cosmological constant, to within a few percent. But these measurements constrain only the present-day value of the vacuum energy density and its behavior over the last 10 billion years. They say nothing about what the vacuum energy was before that, or what it will be in the far future. They do not constrain the mechanism that sets the value. They do not reveal whether the value is dynamical or fixed. And they certainly do not explain why the quantum contribution, which should dominate by 120 orders of magnitude, does not. The quantum field theory prediction is not wrong in the sense of being contradicted by experiment. It is wrong in the sense of being incomplete. The calculation assumes that vacuum energy sums over all quantum modes up to some cutoff, and that this sum contributes to the stress-energy tensor that curves space-time. But perhaps that assumption is too naive. Perhaps there is a physical process, unknown, unmeasured, not yet discovered, that prevents the vacuum energy from gravitating at high energies. Perhaps the cutoff is not the Planck scale, but some much lower scale, for reasons we do not yet understand. Or perhaps the vacuum energy does gravitate, and the enormous quantum contribution is real, but it is cancelled by an equally enormous contribution of opposite sign from some other sector of the theory. In supersymmetry, that other sector is the fermionic vacuum. In other proposals, it might be a classical contribution from the cosmological constant term in the Einstein-Hilbert action, tuned by hand to cancel the quantum piece. But tuning by hand is not an explanation. It is an admission that we do not know why the tuning occurs. String theory offers a different perspective. In string theory, the cosmological constant is not a single parameter, but a function of the vacuum state, the configuration of extra dimensions, the values of moduli fields, the shape of the compactification manifold. The string theory landscape contains an enormous number of such vacuum states, each with a different effective cosmological constant. If the landscape is real, and if a mechanism like eternal inflation explores it, then the observed value is not determined by a fundamental principle, but selected from the ensemble of possibilities. Universes with large vacuum energy density inflate violently and become sterile. Universes with small vacuum energy density inflate gently and allow structure to form. We observe a small value because we are observers, and observers require a small value. This is the anthropic explanation in its most developed form, but it remains controversial. It requires the multiverse to be real, which is untestable. It offers no prediction of the vacuum energy's precise value, only a probabilistic argument that it should fall within the anthropic window. And it does not explain why the landscape exists in the first place, or why eternal inflation populates it, or why the fundamental laws of physics permit such an ensemble. It trades one mystery for another. What does the evidence show? The evidence shows that the vacuum energy density is small and positive. It shows that the expansion of the universe is accelerating. It shows that the simplest model, ΛCDM with a cosmological constant, fits all observations to high precision. It does not show why the value is what it is. It does not show whether the value is fundamental or dynamical. It does not show whether the anthropic explanation is correct. And it does not resolve the 120 order of magnitude discrepancy between the quantum field theory prediction and the measured value. The cosmological constant problem is not a failure of measurement. It is not a failure of observation. It is a failure of theory. Quantum field theory and general relativity, the two most successful theories in physics, make predictions that are mutually incompatible when applied to the ears. Vacuum energy of the universe. One theory says the vacuum energy should be enormous. The other theory says that if it were, the universe would be empty. The universe is not empty. Something is missing from the picture. The vacuum catastrophe has a twin, the horizon problem, and the two are more deeply connected than most treatments acknowledge. Picture the cosmic microwave background as it was mapped by the Planck satellite between 2009 and 2013. The radiation reaches us from every direction in the sky, a nearly uniform glow at a temperature of 2.725 Kelvin. Nearly uniform, but not perfectly. There are temperature fluctuations, hot spots and cold spots, differing by about 1 part in 100,000. Those fluctuations, tiny as they are, seeded the galaxies. Regions slightly denser than average collapsed under their own gravity. Regions slightly less dense expanded into voids. The pattern of fluctuations is preserved in the microwave background, frozen at the moment 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen, rendering space transparent for the first time. The puzzle is the uniformity. The universe at that early time was divided into more than 100,000 causally disconnected patches. Light from one patch had not had time to reach another. No signal, no information, no physical influence could have traveled between them. Yet the temperature across all those patches is the same, to 1 part in 100,000. How did regions of space that had never communicated with each other come to have the same temperature? The standard answer is inflation, a brief period of exponential expansion in the first fraction of a second after the Big Bang, during which the universe grew by at least 26 orders of magnitude in less than 10 to the minus 32 seconds. Inflation stretches a single causally connected patch, small enough that light has had time to smooth out temperature differences, to a size vastly larger than the observable universe today. After inflation ends, that uniformity persists. The cosmic microwave background is uniform because it came from a single patch that was already uniform before inflation began. But inflation requires a scalar field, the inflaton, with a very particular potential energy curve. The field must start high on the curve, roll slowly down, and release its energy into particles and radiation when it reaches the bottom. The slow roll is key. If the field rolls too quickly, inflation ends too soon, and the universe does not expand enough to solve the horizon problem. If the field rolls too slowly, inflation never ends, and the universe remains empty, stretched so thin that no structure can form. The potential must be flat enough to sustain slow roll for at least 60 e-folds, 60 doublings of the scale factor, but steep enough that the field eventually reaches the bottom. This is fine-tuning of a different kind. The shape of the inflaton potential is not predicted by any fundamental theory. It is chosen to fit the observations. And the initial conditions, the starting value of the inflaton field, the homogeneity of space before inflation begins, must themselves be finely tuned. If the universe starts out too inhomogeneous, inflation cannot smooth it. If it starts out with too much kinetic energy, the field overshoots the slow roll region and inflation fails. The parameter space that produces a successful inflationary epoch is narrow, and the energy density during inflation is enormous, comparable to the grand unification scale, roughly 10 to the 16th giga-electron volts. That energy density comes from the potential energy of the inflaton field. When inflation ends, that energy is converted into particles and radiation, reheating the universe. But the inflaton potential energy is, by definition, a form of vacuum energy. During inflation, the vacuum energy density is huge. After inflation, it must drop by more than 100 orders of magnitude to reach the value we observe today. How does that happen? What mechanism causes the vacuum energy to decay from the inflationary scale to the cosmological constant scale? Inflation does not answer this. It shifts the cosmological constant problem to a different epoch. The vacuum energy is large during inflation and small afterward, and no known principle explains the transition or sets the final value. Alan Guth, who proposed the inflationary model in 1980, was aware of this tension. In his original paper, he noted that inflation could solve the horizon and flatness problems, but only if the inflaton potential had the right properties. He described the potential as ridiculously flat and acknowledged that the model did not predict the shape, it assumed it. Andre Linde, who developed chaotic inflation in 1983, explored a wider range of potentials and showed that many could produce successful inflation, but the cosmological constant problem remained. The inflaton field decays, reheating the universe, and the vacuum energy density after reheating must be incredibly small. Linde proposed eternal inflation as a way to generate an ensemble of outcomes. But that returned the explanation to the Anthropic framework. Paul Steinhardt, one of the architects of inflationary cosmology, has become one of its most prominent critics. In a 2011 paper and several subsequent essays, Steinhardt argued that inflation, rather than solving the fine-tuning problems of the Big Bang model, has introduced its own fine-tuning problems and become unfalsifiable. The theory has grown so flexible, accommodating hundreds of different inflaton potentials, each predicting different observable signatures, that it can fit almost any data. When observations rule out one potential, another is proposed. The parameter space is so large that inflation as a framework cannot be ruled out. Steinhardt calls this a crisis. A theory that can explain anything explains nothing. What does it mean that the two great fine-tuning problems of cosmology, the cosmological constant and the initial conditions for inflation, both reduce to the question of why the vacuum energy has the value it does at different epochs? The vacuum energy today is dark energy. The vacuum energy during inflation is the inflaton potential. Both are scalar fields. Both have energy densities that do not dilute with expansion. Both drive accelerated expansion. The difference is only the scale. During inflation, the vacuum energy density is 120 orders of magnitude larger than it is today. The transition between the two regimes is not explained. The mechanism that sets the inflaton potential is not known. The mechanism that sets the cosmological constant is not known. And the relationship between them, if any, is not understood. String theory, again, offers a landscape of possibilities. Different compactifications of the extra dimensions correspond to different inflaton potentials and different cosmological constants. If eternal inflation explores the landscape, some regions undergo inflationary expansion with high vacuum energy, then decay to lower energy vacua with smaller cosmological constants. Observers arise in the regions where the cosmological constant is small enough to permit structure formation. This picture unifies the anthropic explanations of inflation and dark energy, but it remains speculative. No prediction of string theory has been confirmed experimentally, and the landscape itself is inferred from theoretical considerations, not observed. Consider the alternative. Suppose the vacuum energy is not a free parameter, not a landscape of possibilities, but determined by a fundamental principle we have not yet discovered. Suppose there is a symmetry, deeper than supersymmetry, that enforces a cancellation between the quantum contributions to the vacuum energy and some classical or gravitational contribution. Such a symmetry would have to be extraordinarily precise, cancelling 120 orders of magnitude, and it would have to be broken in exactly the right way to leave the small residual we observe. No such symmetry is known. No candidate mechanism has been proposed that does not reintroduce fine-tuning at another level. Or suppose the vacuum energy does not gravitate in the way general relativity predicts. Suppose there is a modification to the Einstein field equations, active only at the scale of the vacuum energy density, that decouples the quantum vacuum from space-time curvature. Such a modification would have to preserve all the successes of general relativity: planetary orbits, gravitational lensing, black hole dynamics, gravitational wave propagation, while altering only the cosmological response to vacuum energy. Again, no such modification is known. Proposals exist, but all face severe constraints from observations. The Large Hadron Collider, which discovered the Higgs boson in 2012, has not found supersymmetric particles. It has not found extra dimensions. It has not found any new physics beyond the standard model of particle physics, despite searching at energy scales up to 13 tera-electron-volts. The standard model, which describes the electromagnetic, weak and strong forces and all known particles, is remarkably successful. It predicts the masses of particles, the strengths of interactions, and the outcomes of high-energy collisions with extraordinary precision. But the standard model does not include gravity. It does not predict the cosmological constant, and it does not explain why the Higgs field, which is also a scalar field with a vacuum expectation value, does not contribute a vacuum energy density comparable to the Planck scale. The Higgs vacuum energy problem is a smaller version of the cosmological constant problem. The Higgs field has a non-zero value in the vacuum, about 246 giga-electron-volts. That value sets the masses of the W and Z bosons, the carriers of the weak force. But the energy density associated with the Higgs vacuum, calculated from quantum field theory, should be enormous, comparable to the fourth power of the cutoff scale, just as for any other field. If the cutoff is the Planck scale, the Higgs contribution alone would be 10 to the 120th times larger than the observed cosmological constant. Somehow, that contribution is cancelled or does not gravitate. The same problem at a different scale. Supersymmetry was invented, in part, to address the Higgs vacuum energy problem. In a supersymmetric theory, the quantum corrections to the Higgs vacuum energy from fermions and bosons cancel, stabilizing the Higgs mass at the electroweak scale rather than letting it run up to the Planck scale. This is called the hierarchy problem. Supersymmetry solves it by imposing a symmetry that controls the corrections. But supersymmetry, as I have said, is not observed. If it exists, it is broken, and the breaking reintroduces fine-tuning. The cancellation is no longer automatic. It requires the breaking scale to be chosen carefully, and no principle dictates that choice. What happens to the vacuum energy when a symmetry breaks? Consider a simple analogy. Picture a pencil balanced on its tip. The configuration is symmetric. The pencil could fall in any direction, but unstable. The slightest perturbation causes the pencil to fall, breaking the symmetry. Once it falls, the pencil lies in a particular direction, and the symmetry is gone. The vacuum, in quantum field theory, behaves similarly. A symmetric vacuum is often unstable. A field can sit at a high-energy symmetric point for a while, but quantum fluctuations eventually push it to a lower energy state, breaking the symmetry. When the symmetry breaks, the field settles into a new vacuum with a lower energy density. The energy difference between the symmetric and broken vacua is released. In the early universe, symmetry-breaking events released energy that contributed to the particle content and the expansion rate. The electroweak symmetry breaking, which gave mass to the W and Z bosons, occurred at a temperature of about 159 giga-electron volts, roughly 10 to the minus 11 seconds after the Big Bang. The energy released during that transition contributed to the radiation density at the time. But after the transition, the Higgs field settled into its new vacuum, and the energy density of that vacuum, the Higgs vacuum energy, should still be present today, contributing to the cosmological constant. It is not. Or rather, it is cancelled by something, and we do not know what. The same logic applies to every other field in the Standard Model. The vacuum energy of the electron field, the quark fields, the gluon fields, all should contribute to the cosmological constant. All are calculated to be enormous. All are observed to be negligible. Every field, every particle, every interaction adds to the sum, and the sum should be catastrophic. Yet the total is tiny. Something enforces a cancellation across all fields, across all energies, with a precision of 120 orders of magnitude. No known principle does this. Steven Weinberg, in his 1989 paper on the cosmological constant and the anthropic principle, calculated that if the vacuum energy density were larger than about 10 to the minus 9 joules per cubic meter, galaxies would not form. Above that threshold, the repulsive effect of dark energy would overpower the attractive pull of gravity before. Density fluctuations could collapse into bound structures. The observed value is about 6 × 10⁻10 joules per cubic meter, safely below the threshold, but not by a huge margin. Weinberg argued that this rough agreement, the observed value lying near the upper edge of the anthropic window, was evidence for anthropic selection. In a multiverse where the cosmological constant varies, most observers would find themselves in universes where the value is near the upper limit, because such universes maximize the volume of space-time in which observers can exist. This argument has been debated extensively. Some physicists find it compelling. Others reject it as unfalsifiable and philosophically unsatisfying. The debate centers on whether the multiverse is a scientific hypothesis or a metaphysical speculation. If other universes are fundamentally unobservable, can invoking them constitute an explanation? Does anthropic reasoning provide predictive power, or does it merely fit the data after the fact? In 2006, Raphael Bousseau and Joseph Polchinski published a detailed analysis of the string theory landscape and its implications for the cosmological constant. They argued that the landscape contains enough vacuum states, conservatively at least 10 to the 500th, that a statistical distribution of cosmological constants is guaranteed. Most states have large positive or large negative values, rendering them inhospitable to structure. But a small fraction have values near zero, and within that fraction, some have values small and positive, consistent with observations. Bousseau and Polchinski calculated that the probability of finding a vacuum with a cosmological constant in the observed range, given the landscape and anthropic selection, is not absurdly small. The prediction is not precise. It does not single out the exact value, but it is not in conflict with the data either. This is the strongest form of the anthropic argument. It does not merely assert that we observe a small cosmological constant because we could not exist otherwise. It provides a framework, string theory plus eternal inflation, in which a distribution of values is predicted, and it shows that the observed value is probable within the subset of values compatible with observers. But the framework itself is not confirmed. String theory has not made a testable prediction. Eternal inflation has not been directly observed. The landscape is inferred, not measured. The argument rests on layers of theoretical speculation, and each layer introduces uncertainties. What would it take to confirm or rule out the anthropic explanation? One test would be to measure the cosmological constant more precisely and determine whether it is exactly constant or evolving slowly over time. If the value is changing, that would rule out a true cosmological constant and point toward a dynamical field like quintessence. If the value is constant, that does not prove the anthropic explanation, but it would be consistent with it. The Dark Energy Survey, which observed 300 million galaxies between 2013 and 2019, measured the equation of state parameter W to be -0.978, with an uncertainty of about 0.03. The value is consistent with -1, the cosmological constant, but a small deviation is not yet ruled out. Future surveys, the Vera C. Rubin Observatory's Legacy Survey of Space and Time, the Euclid satellite, the Nancy Grace Roman Space Telescope, will measure W to percent-level precision or better. If W differs from -1, the cosmological constant is not constant, and the landscape of explanations changes. Another test would be to discover new physics at accessible energy scales. If supersymmetry exists, and the superpartners have masses below a few tera-electron volts, they might be discovered at the high-luminosity Large Hadron Collider, scheduled to begin operations in 2029. The discovery of supersymmetric particles would not solve the cosmological constant problem. Broken supersymmetry still requires fine-tuning. But it would confirm that the hierarchy problem has a solution, and that might provide clues about how nature handles fine-tuning more generally. Conversely, if no new physics is found up to the highest accessible energies, that would strengthen the case that the Standard Model is the complete low-energy description, and that the cosmological constant is a parameter that must be measured, not calculated. A third test, more speculative, would be to detect signatures of other universes. Some models of eternal inflation predict that bubble universes, nucleating and expanding, occasionally collide. If our universe collided with another in the distant past, the collision might have left an imprint in the cosmic microwave background. A circular pattern of temperature fluctuations, a cold spot larger than expected from random fluctuations. Searches for such signatures have been conducted, and none has been confirmed. But the absence of evidence is not evidence of absence. The probability of a detectable collision depends on the rate of bubble nucleation, the age of the multiverse, and the size of the observable region, all unknown. A collision signature would be extraordinary evidence for the multiverse. The lack of one does not rule it out. The ultimate fate of the universe is determined by the vacuum energy. If the cosmological constant is exactly constant, the expansion will continue to accelerate forever. Galaxies outside our local group, the Milky Way, Andromeda, and a few dozen smaller galaxies bound by gravity, will recede beyond the cosmic horizon, disappearing from view as space expands faster than light can cross it. Within a few 100 billion years, distant galaxies will have redshifted to invisibility. The cosmic microwave background will cool and fade. The universe will grow dark and cold. Stars will continue to form from the gas in galaxies for another 100 trillion years, but the gas supply is finite. Once it is exhausted, star formation will cease. Existing stars will burn out. White dwarfs will cool into black dwarfs. Neutron stars will remain as they are, cold and inert. Black holes will persist, slowly evaporating through Hawking radiation, a quantum process in which virtual particles near the event horizon become real, one escaping, one falling in, causing the black hole to lose mass over immense timescales. A black hole with the mass of the Sun will evaporate in 10 to the 67th years. A supermassive black hole with 1 billion solar masses will evaporate in 10 to the 100th years. After all black holes have evaporated, the universe will contain only isolated particles, photons, neutrinos, electrons, positrons, spread so thinly that interactions become vanishingly rare. This is the heat death. But even the heat death is not the final state. In a universe with a positive cosmological constant, there is a de Sitter horizon, a boundary beyond which no information can ever reach an observer. As the expansion accelerates, the horizon shrinks. Particles beyond the horizon are causally disconnected, and their information is lost. The horizon itself has a temperature, analogous to the temperature of a black hole horizon, called the de Sitter temperature. That temperature is incredibly small, about 10 to the minus 30 Kelvin for the observed cosmological constant, but it is not zero. The horizon emits Hawking radiation, a faint thermal glow. Over timescales longer than 10 to the 120th years, that radiation could, in principle, fluctuate into complex structures, virtual particles, fields, even Boltzmann brains, observers that arise spontaneously from random thermal fluctuations. But these are transient and exceedingly rare. If the vacuum is not stable, if it is a false vacuum, metastable, waiting to decay, the fate is different. A false vacuum is a local minimum of the potential energy, not the global minimum. The field sits in the false vacuum for a long time, but quantum tunneling can push it to the true vacuum. When that happens, a bubble of true vacuum nucleates and expands at the speed of light, converting the false vacuum into the true vacuum as it grows. The energy difference between the two vacua is released, potentially reheating the universe, or, if the true vacuum has negative energy density, collapsing space. This is vacuum decay. Calculations by Sidney Coleman and Frank DeLucia in 1980 showed that vacuum decay, if it occurs, is catastrophic. The bubble wall sweeps through space, obliterating everything in its path. The transition can happen at any time, without warning, triggered by a random quantum fluctuation. The probability of decay depends on the height and width of the potential barrier separating the false vacuum from the true vacuum. If the barrier is high and wide, the tunneling rate is low, and the false vacuum can persist for timescales far longer than the current age of the universe. If the barrier is low or narrow, the tunneling rate is high, and the false vacuum is short-lived. Is the vacuum we inhabit stable, metastable, or unstable? The answer depends on the precise values of the Higgs boson mass and the top quark mass, both of which affect the shape of the Higgs potential at high energies. Measurements of the Higgs mass, 125.25 giga-electron volts, and the top quark mass, about 173 giga-electron volts, place the standard model vacuum in the metastable region. The potential has a local minimum at the electroweak scale, where we live, and a deeper minimum at energies around 10 to the 10th giga-electron volts. The barrier between them is high enough that the tunneling rate is extremely low. The lifetime of the vacuum is estimated at 10 to the 600th years or more, vastly longer than the current age of the universe, 13.8 billion years. We are safe, for now. But the calculation is sensitive to the precise values of the masses and to corrections from physics beyond the standard model. If supersymmetry exists, even if broken, it could stabilize the vacuum, raising the barrier and preventing decay. If new particles exist at intermediate energies, they could alter the running of the Higgs coupling, changing the shape of the potential. The fact that we observe a metastable vacuum rather than a stable or unstable one is another coincidence. If the top quark mass were a few giga-electron volts lighter, the vacuum would be stable. If it were a few giga-electron volts heavier, the vacuum would have decayed long ago. The measured values place us near the boundary. What does it mean that the universe sits at the edge of stability? That the cosmological constant sits at the edge of the anthropic window? That the top quark mass sits at the boundary between stability and decay? Are these coincidences, or are they clues? One interpretation is that we are seeing the consequences of a selection effect operating at multiple levels. Universes with unstable vacua decay before observers arise. Universes with large cosmological constants expand too quickly for structure to form. Universes with top quark masses far from the observed value either collapse or remain empty. The parameter space that supports observers is narrow, and we observe the values we do because we could not observe anything else. This is the anthropic explanation applied broadly, beyond just the cosmological constant, to the entire set of physical parameters. Another interpretation is that the coincidences are evidence of fine-tuning by an external agent or principle. If the parameters are not random draws from a distribution, but chosen or constrained by something, the narrow windows and near boundary values make sense. But this interpretation introduces its own questions. What is the agent or principle? Why does it favor observers? How does it set the parameters? The interpretation offers no mechanism, no testable prediction, no way to distinguish it from the anthropic explanation. A third interpretation is that the coincidences are artifacts of incomplete understanding. The parameters we measure may not be fundamental. They may be effective low-energy values that arise from a more fundamental theory with fewer parameters or none. In such a theory, the relationships between parameters might be constrained by symmetries or dynamical principles, reducing the apparent fine-tuning. String theory aims to be such a theory, but it has not yet delivered the constraints. Loop quantum gravity, causal set theory, and other approaches to quantum gravity attempt to derive spacetime and its properties from more fundamental structures, but none has made contact with the cosmological constant problem. The physicist John Wheeler once asked, "Why the quantum?" He wanted to know why the universe is quantum mechanical, why nature obeys the rules of probability and superposition rather than determinism. He imagined that the answer might lie in self-consistency, that the universe explains itself, that the laws of physics are the only laws compatible with the existence of observers capable of discovering them. This is participatory anthropic reasoning, a loop in which the universe requires observers to exist and observers require the universe to have certain properties. The loop closes. The parameters are what they are because nothing else permits the loop. Wheeler's vision is poetic but vague. It does not specify the mechanism by which the loop operates, or how to calculate the parameters from the requirement of self-consistency. It shifts the question from why these values to why observers. The latter question is no easier. The cosmological constant problem sits at the intersection of quantum mechanics, general relativity, and cosmology. It is a problem of scales: the Planck scale, the electroweak scale, the cosmological scale, separated by enormous factors, and no known principle relates them. It is a problem of cancellation. The quantum contribution and the observed value differ by 120 orders of magnitude, and no symmetry enforces the cancellation. It is a problem of coincidences. The value lies near the anthropic bound, near the boundary of vacuum stability, at a time when matter and dark energy are comparable. And it is a problem of explanation. What counts as an explanation when the multiverse is invoked, when fine-tuning is accepted, when the parameters are measured rather than derived? Think about what it would mean to solve this problem. A solution would be a theory or a principle that predicts the value of the cosmological constant from more fundamental inputs without invoking fine-tuning or anthropic selection. The theory would have to explain why the quantum contributions cancel to 120 orders of magnitude. It would have to explain why the residual value is small and positive. It would have to explain the timing, why dark energy dominates now and not earlier. And it would have to make other predictions, testable predictions, that could confirm or rule it out. No such theory exists. The closest candidates, supersymmetry, string theory, modified gravity, all fall short. Supersymmetry does not predict the cosmological constant. It requires fine-tuning to match the observed value. String theory offers a landscape and anthropic selection, not a unique prediction. Modified gravity has been constrained by gravitational wave observations and does not eliminate the need for dark energy. The problem remains open. In 2019, a team led by Riess used the Hubble Space Telescope to measure the current expansion rate of the universe, the Hubble constant, with unprecedented precision. The value they obtained, 74 kilometers per second per megaparsec, differs from the value inferred from the cosmic microwave background by the Planck satellite, 67 kilometers per second per megaparsec. The discrepancy is statistically significant, more than 5 standard deviations, and it has persisted across multiple independent measurements. This is the Hubble tension. The Hubble tension might be a systematic error, a problem with the calibration of standard candles, or the modeling of the cosmic microwave background. Or it might be evidence of new physics. If the dark energy density was different in the early universe, or if an additional component of dark energy exists that behaves differently at different epochs, the expansion history would be altered, and the Hubble constant derived from early universe data would not match the local measurement. Some models of dynamical dark energy can resolve the tension, but they introduce new parameters and new fine-tuning. Alternatively, the tension might indicate that the universe is not as homogeneous as the ΛCDM model assumes. If we live in a region where the matter density is slightly lower than average, a void, the local expansion rate would be higher than the global average. Observations of the large-scale structure are beginning to test this possibility, and so far they do not support it. The distribution of galaxies appears consistent with homogeneity on scales above 100 megaparsecs. But the measurements are ongoing, and the picture may change. The Hubble tension is a reminder that the ΛCDM model, successful as it is not the final word. It fits the data, but it is not a theory. It is a phenomenological description with 6 parameters, each measured but none derived. The cosmological constant is one of those parameters. If the tension is resolved by modifying ΛCDM, the cosmological constant problem might take a different form, but it will not go away. The quantum field theory prediction will still be 120 orders of magnitude too large, and the question of why the suppression occurs will remain. What would change if the vacuum energy were measured to be evolving? A detection of time-dependent dark energy, a value of the equation of state parameter W that differs from -1, or a measurement showing that W itself changes over cosmic time, would rule out a cosmological constant and require a dynamical explanation. Quintessence, or some variant, would become the leading candidate. The quintessence field would have to be extraordinarily light, its mass on the order of 10 to the minus 33 electron volts, to produce an energy density and pressure comparable to the observed dark energy. Such a light field is difficult to reconcile with particle physics. Fields that light are vulnerable to quantum corrections that push their masses up to much higher scales. Keeping the mass small requires a symmetry, and no suitable symmetry is known. This is the quintessence fine-tuning problem, analogous to the cosmological constant problem, but focused on the field's mass rather than its energy density. Some models of quintessence invoke tracker fields, fields whose dynamics naturally drive them toward an attractor solution, independent of initial conditions. A tracker field can mimic a cosmological constant today, even if it behaved differently in the past. And it can alleviate the coincidence problem by entering the tracking regime only recently in cosmic history. But tracker models do not eliminate fine-tuning. The shape of the potential and the parameters of the attractor must still be chosen to fit the data. Other models invoke symmetries that protect the field from large quantum corrections. Shift symmetries, for example, forbid mass terms and restrict the form of the potential, keeping the field light. But shift symmetries are approximate at best, and breaking them reintroduces the corrections. No model has succeeded in deriving a naturally light scalar field from first principles without fine-tuning. The cosmological constant problem is often called the vacuum catastrophe, because the failure of theory is so dramatic. A prediction off by a factor of 2 is a problem. A prediction off by a factor of 10 is a crisis. A prediction off by a factor of 10 to the 120th is unprecedented. No other prediction in physics has been this wrong. And yet, the problem is not treated as a refutation of quantum field theory or general relativity. Both theories remain extraordinarily successful in their respective domains. Quantum field theory predicts the anomalous magnetic moment of the electron to 1 part in a trillion. General relativity predicts the precession of Mercury's orbit, the bending of light by the Sun, and the waveform of gravitational waves from merging black holes, all confirmed to high precision. The theories work. They are not wrong. But they are incomplete, and the incompleteness is most glaring in the vacuum energy. What does it mean that the 2 pillars of modern physics, quantum mechanics and general relativity produce a catastrophic prediction when combined, and the resolution is not known. It means we are missing something fundamental. The vacuum is not what we think it is, or gravity is not what we think it is, or the relationship between them is not what we think it is. The answer may lie in quantum gravity, the theory that unifies quantum mechanics and general relativity. But quantum gravity is not yet complete. String theory is a candidate, but it is not confirmed. Loop quantum gravity is a candidate, but it has not made testable predictions. Other approaches exist, but none has resolved the cosmological constant problem. Perhaps the problem cannot be resolved within the framework of physics as we currently understand it. Perhaps the question, why this value, is not a question physics can answer, any more than physics can answer, why these laws, or why is there something rather than nothing? These are boundary questions, questions at the edge of what empirical science can address. They may require a different kind of explanation, metaphysical, philosophical, or acknowledged as brute facts. Or perhaps the resolution is closer than it seems, hidden in a symmetry we have not yet discovered, a principle we have not yet articulated, a calculation we have not yet performed. The history of physics is full of problems that seemed intractable. The ultraviolet catastrophe, the stability of atoms, the source of stellar energy, that were resolved by new theories that reframed the question. The cosmological constant problem may be waiting for its quantum mechanics, its nuclear physics, its general relativity. For now, it waits. Let me bring this exploration to a close. I have walked you through the structure of the cosmological constant problem, from its quantum field theory roots to its cosmological consequences. The vacuum, far from being empty, seethes with quantum fluctuations. Every field contributes to the vacuum energy density, and the sum, calculated to the Planck scale, yields a number on the order of 10 to the 113 joules per cubic meter. General relativity requires that energy to gravitate. If it did, the universe would have torn itself apart in a fraction of a second. The observed vacuum energy density, inferred from the accelerating expansion measured by type 1a supernovae, the cosmic microwave background, and baryon acoustic oscillations, is approximately 6 times 10 to the minus 10 joules per cubic meter. The discrepancy is 120 orders of magnitude, the worst prediction in physics. No known mechanism explains the suppression. Supersymmetry, if exact, would cancel the quantum contributions. But supersymmetry is broken, and the breaking reintroduces fine-tuning. The anthropic principle, combined with the string theory landscape and eternal inflation, offers a framework in which the observed value is selected from a vast ensemble. But that framework is speculative and untestable. Modified gravity theories attempt to reproduce acceleration without dark energy, but observations constrain them severely. Dynamical dark energy models introduce scalar fields that evolve over time, but they shift the fine-tuning to the field's initial conditions and potential without eliminating it. The vacuum energy determines the fate of the universe. If it is a cosmological constant, the expansion will accelerate forever, driving galaxies beyond the cosmic horizon, extinguishing star formation and leaving the universe cold, dark, and empty, the heat death. If the vacuum is metastable, it could decay in the far future, nucleating a bubble of true vacuum that expands at light speed, obliterating all structure. The standard model vacuum is metastable, with a lifetime far exceeding the current age of the universe, but the calculation depends sensitively on the Higgs boson mass and the top quark mass, both of which place us near the boundary of stability. What the evidence shows is that the vacuum energy is small, positive, and consistent with a cosmological constant. The expansion is accelerating. The ΛCDM model fits all observations to percent-level precision. The universe is hospitable to structure, and we exist within the narrow window of cosmic history where matter and dark energy have comparable densities. The coincidence is striking. What the evidence does not show is why. Why the vacuum energy has the value it does. Why the quantum contributions are suppressed by 120 orders of magnitude. Why the parameters of the universe fall within the narrow ranges that permit observers. The cosmological constant problem remains unsolved. Something cancels the quantum vacuum energy almost perfectly, but not quite. The residual drives the accelerating expansion. We do not know what that something is. We do not know whether it is a symmetry, a selection effect, a principle we have not yet discovered, or something else entirely. The vacuum is calm enough for galaxies to form, for stars to ignite, for planets to cool, for life to begin. That calmness, that suppression, is not explained by any calculation we trust. Something prevents the quantum vacuum from tearing the universe apart. We do not know what it is. If you found value in this exploration, consider subscribing. It helps these deep dives reach more curious minds willing to sit with unresolved questions. This video touched on the accelerating expansion of the universe, the observational signature of dark energy. The nature of that acceleration and what it reveals about the fate of the cosmos is explored more fully in another piece. You will find it on the end screen and in the description, if the question holds your attention. Sleep well tonight, standing on ground that should not exist, in a universe held together by a cancellation no one can explain. Good night.